Good morning, everybody. I just want to introduce to you our illustrious Dr. John Bristow, matriculated from Escort High School in 1969, completed a BSc Geology Honours degree in 1974, and MSc in Geology in 1977 at the University of Natal, and a PhD in geochemistry at UCT at 1980. Labored with all these titles, his studies then followed 2 years as a postdoc at the University of New Mexico in Albuquerque in 1981 and 82, from where he traveled extensively researching volcanic rocks and US kimberlites. He joined the Anglo-American De Beers Group in 1983, and he worked primarily on kimberlites and diamond geology exploration and research for 12 years. Before leaving to set up his own business, his geological work and interest have taken him and the family to most of the world's continents and remote places, and still active in the diamond and mineral policy sectors, and a resident at Hermanus with his wife Marilyn, where he's actually the founder member of the Overberg Geotechnical Group as well. Here we go, John. It's a pleasure to introduce John.
Thanks, Henny. I think we're a Geoscientists group that put up with some of you, geotechnical people in the process. Anyway, thanks for the introduction, and thanks everyone for tuning in this morning. You'll have gathered from that introduction by Henny that I was a long-time professional student. And in that period, I was lucky enough to do an MSc on the Lubombo volcanics, effectively the Karoo volcanics that we find up our eastern boundary of South Africa, adjacent to Mozambique. So I started on the Lubombo volcanics, which they kick off at Pangeni and they go up to Hluhluwe, and then they turn north and go up to the Swazi border. And many of you, I'm sure, going to Mozambique or that part of the world would have noticed the very impressive Lubombo Mountains. Anyway, we were part of a Karoo geodynamics project at that period. Two colleagues out of Oxford University worked on the Swaziland section and mapped it and documented the geology there. And then I was fortunate enough to do the rest of the Lubombo, which stretches all the way up to the Limpopo River through the Kruger National Park. So I had a great couple of years mapping and walking all the rivers in the Kruger Park, and met some really good people there, and also worked extensively with the soil scientists. So where we couldn't see the geology, we would use Freek Venter and a few other people to fill in the gaps for us by looking at the soils and the vegetation and even the animals and birds. There's a very close association with the geology. So I'm going to talk today about Mt St Helens. Many of you will have heard about it and perhaps seen some of the pictures. It was a spectacular volcanic event back in 1980, May 1980, or May 18 in particular. And so we'd moved to Albuquerque in New Mexico, where I did a postdoc 1981-82. And I'd been invited or given an office there by a lovely fellow, Professor Wolf Alston, who was a volcanologist. He'd worked on the volcano immediately after the cataclysmic eruption in May 18, and I was very fortunate to spend time with him looking at all his samples and then working, or he would take us out. There are wonderful volcanic exposures all over New Mexico and the southwest US, and that's sort of the area that I focused in, but we traveled extensively in that period and had a great time. So I'm going to take you through this presentation. It's lots of pictures. There is some text. I'm not going to get too involved in the detail of the text. You're all welcome to the presentation if you want to, particularly those of you working on volcanics, and then we'll also put this on YouTube. So let's get on with the show. Just the structure, I'm going to do a very quick run through Earth structure and particularly plate tectonics, so 101, a bit of igneous petrology, a refresher for most of us who've forgotten about it. Talk about lavas, volcanoes, and the role of water in general, just so that we understand why these different volcanic events show different features. And then we'll spend a lot of time, obviously, or most of the time, on the actual eruption. look at the deposit types, the casualties, the hazards, and the ongoing monitoring that sort of come out of this work. And then just loop back to the Lubombo again. There's a gorgeous volcanic complex in the southern part of Mkuzi Game Reserve, sort of sitting on the top of the Lubombo. It stretches across to Pinda, the Pinda Game Reserve now. And if you look at the slide on the top right, you'll see an airfall tephra, or an airfall deposit, which is 133 million years old. And down below, the Mt St Helens airfall tephra, which is only 41 years old. And if you sort of looked at them in a box, without your setting, you'd be hard pressed to tell, which was which. But that's the nature of these rocks, and that's what I'm going to talk about. Sorry. Okay, so let's just make sure we know of the setting. So the setting that we're going to focus on this morning is this northwest part of the American plate, where I've got the blue circle. It's on the northeast edge of the Pacific plate. And on the slide, you'll see the structure of our Earth sort of laid down on a piece of paper with all these numerous plates and the mid-ocean spreading ridges between them. And if we go and look at this slide, it's more detailed. In fact, it's rather detailed, but again, it just gives you a very good impression of how our globe looks. And for us sitting down here and boring Southern Africa, or for that matter, Africa, we don't have much volcanic activity. In fact, we don't have any in our part of the world. We now and again had the odd minor earthquake. There were 2 small quakes, as you'll be aware, late last year off the Cape Coast, and there was one out in the Indian Ocean, probably on the actual ridge. But the real action in terms of plates is this amazing Pacific plate and what's known as the Pacific Ring of Fire. And if you look around, you'll see all these triangles, which are effectively earthquake activity, and many of them also volcanoes. And then you'll see the spreading ridge, or the spreading ridges. There's the Indian Ocean spreading ridge here on the right-hand side. And then if you come across into the Pacific plate, you have a series of subduction zones. The blue line, thick blue line, is where the Pacific plate is subducting or being pushed under the different plates off to the west and to the north and to the east, with some variability, and we'll come to that on the next set of slides. So again, Mt St Helens is sitting here in the Cascades area up in Oregon and Washington State. Across on the left-hand side here, you'll just, I'm sure have noticed or heard, on the 14th of February this year, off the coast of Fukushima again, was another 7.3 magnitude earthquake, which was very similar to the one of 2011, but the big difference that time was there was a huge tsunami. There was a piece of the seafloor which moved about 50 meters, and that you can imagine, throw a stone into your swimming pool and you'll get a small tsunami. It's a very small wave, but if you imagine, throwing a much bigger rock in there, you obviously get a bigger tsunami. Now you go to the seafloor and you move a chunk of the Earth's plate 50 meters, it causes huge disturbance in the water. And that was the tsunami that flattened the Fukushima nuclear plant and did huge damage. And we saw pictures of boats running down the streets or floating down the streets. So a very active part of the world is the Pacific plate. If we just, so that was the plan. This is a cross-section. Again, it's just useful to put things in context because it also helps explain why Mt St Helens is where it is. If you look at this cross-section, here in the middle is the oceanic spreading ridge. So to go back one, that would be this very sort of offset and zigzaggy line here and up through the Indian Ocean. So there we have the spreading plate. So there's new magma being pushed out onto the seafloor. That gets pushed aside and eventually becomes the subduction zone. So as it cools and sinks and comes up against the colder, more buoyant continents, it gets pushed under. So this is basaltic material. Out here to the west, again, you have this magma, or as we call it, the lithosphere spreading. You get things like the Hawaiian Islands, a shield volcano or shield volcano sitting on hotspots. And then again, on the other side, you typically would get a subduction zone and these stratovolcanoes. The one thing that's important in all of this is the role of water, and we'll come back to that. So Mt St Helens and all the other Cascades volcanoes, and there are over 20 of them, sit on the top or at the top of a subduction zone. You have this slab being subducted. That slab, as you can imagine, as it moves across the ocean floor, there's a lot of alteration, water alteration, formation of serpentinite. So this slab ends up with a fair amount of water, either locked up or typically locked up in that sort of hydrous phases or hydrous minerals. And it'll be, mostly in molecular form. When that magma slab or that old slab gets deep enough, that water wants to get out of there, and that water will typically cause the melting. So water lowers the melting temperature. And what happens, you'll get small pods of magma leaving the depth, maybe 25, 35 kilometers, moving up to the base of the crust and probably ponding, and then ultimately it's those sort of magma chambers that lead or give rise to the Mt St Helens activity of the world. And then out on sort of in the continent or the continental plates, we will also have melting once in a while, and typically that is more basaltic and forms very large igneous provinces, LRPs as we call them, and big volcanic outpourings like the Karoo volcanics. Okay, let's also just look so that we understand look at the composition of magmas, because the magma composition ultimately sort of dictates how the magma and the material behaves. So if we look here at this chemistry, it is a key factor. Water is a key factor, and the other big factor in driving volcanic activity, particularly the type we're going to look at this morning, is obviously steam. So across on the right-hand side, we get the sort of common rocks that make up most of our globe and the crust. So we get basalts here, which typically have iron in the range 48 to 52%. You can see it again down here on the bar chart at the bottom. So that basalt tends to be produced in a very hot, mobile environment. And then on the other side of this diagram, so you'll see there low resistance to flow, thin, runny lava. Okay, and that's basalt, and I'll show you some pictures in the next couple of slides to distinguish this. Across on the right-hand side, and basalt, it's equivalent. If this magma forming a basalt doesn't make it to the surface, typically it will form, or it will crystallize and form big gabbroic sills or dolerite dikes, or even things like the bushveld. So the bushveld is essentially a basaltic composition, large magma body that crystallized at depth, and obviously it has a much coarser crystal structure. Across on the right will be rhyolites. These are sort of rocks with about 68 to 77%, let's say average 70% of silica, and they will melt at much lower temperatures, anywhere from sort of 600 to 900 degrees centigrade. But they tend to be very, very sticky. They have a high resistance to flow, and they are the rocks that typically form these amazing composite volcanoes and explosive events. So this is quite important as regards where we're going. And if you look down below here, Hawaiian basalts are a very, very common type of rock out in the ocean. They form most of the ocean floor. They form the basaltic islands. They form the big Karoo volcanic successions. We've got the Ventersdorp volcanics and so on. Typically 50% magnesium oxide, about 13% aluminium. and then, sorry, I beg your pardon, 48% silica. I've got it the wrong way around. So 48%, 50% silica, which is our glass windows, 13% aluminium, and 11% iron. And then on the flip side, the more silicic rocks, the rhyolites and the dacites, 66 or 64 to say 70% silica, 17% aluminium. So again, higher aluminium, also sticky stuff, and then much lower iron. So just to get my facts right, basalt, 40% iron, 40% silica, rhyolite 70% silica, and so basalt is high iron and low silica. Right. So that's let me move on so I can actually show you. So here, for example, are basaltic magmas and what they look like. So these are the rocks that make up the Hawaiian Islands, those very flat islands, very broad, flat shield volcanoes. And you'll see, for example, the base here, 120 kilometers, just to give you scale. That's how sort of effusive and extensive these volcanic features are. And the basalt flows. These two pictures were from the volcanic activity, I think it was in 2019, if I'm correct, where you had lava, basaltic lava flowing down the streets of this island in Hawaii and eating up the vegetation and some houses along the way. So very liquid, and it flows for miles. And when it falls into water, you'll typically see those lovely pictures of pillow lavas forming. And again, on the right-hand side, you'll see Hawaiian lava flow, which has just happened. Again, that's from a couple of years back. So those are basaltic lavas, low silica, high iron. If we then move on, and this is where we're going today, this is this is a typical composite volcanic event or feature. So here we're looking at very silicious magmas, lower temperature magmas, higher silica, 66, 70%. They're sticky, they're viscous, they create steep-sided composite volcanoes. And this cartoon down the left-hand side is almost schematically what Mt St Helens looks like and has looked like. Obviously, it's changed a bit since the major eruption. So you can see here a composite volcano, very steep-sided, lots of different rock types. You've got lava domes, you've got big ash columns, and you've got debris flows, collapses when the volcanoes, as you imagine, get too steep. The sides tend to collapse and form big landslides. They form mud flows, lahars, or mud flows, which can be extremely destructive. And the other important part to note is, again, the role of water. Water plays a big role in the whole construction and volcanic activity of these volcanoes. And on the right-hand side, you'll see a Plinian, an ash column being blown out of Mt St Helens. This was post the May 18 eruption. And down below on the right-hand side, you can see an ash fall deposit where you see all these numerous particles of pumice, basically. And this one's actually very, very well graded. So down the bottom, you have a mostly finer material, and then the sort of coarser, heavier pumice material was deposited first, and there are probably lithic fragments in there as well. And then the lighter material obviously stayed afloat for longer and eventually settled, so that you see this very nice grading. So this left-hand side diagram is exactly what Mt St Helens would have looked like, and that too also shows the various rock types. The other fascinating thing about this for stratigraphers, we geologists like things that are flat lying. If we look around the Cape here, everything's flat and easy to sort of document. If you take this volcano and if you cut a line sort of across the middle of it, you have this fascinating situation of multiple rock types, all probably formed, within maybe 1,000 or a couple of 100,000, like Mt St Helens, and you cut it off there and you start doing stratigraphy. Well, it gets to be quite fun because you can have ash clouds or ash deposits. You can have lava domes, which will be coarsely brecciated rhyodacite or dacite or rhyolite. And then you'll have lahars, muddy flows, and you'll have a whole complex set of rocks. And you can imagine too, when these things get hot and you have magma rising into the base of the volcano and all the snow melt and the glaciers on top of them melting, you also have the ability to move, large amounts of rock material through water action. Okay, let's move on. So this is Mt St Helens, 2,950 meters, nearly 3,000 meters. So it's up in the snow line, and this is prior to May 18, 1980. And then behind it, and interestingly, we'll finish the presentation looking at Mount Rainier, is Mount Rainier, and again, it's over a kilometer and a bit higher than Mt St Helens. And on this slide, obviously the winter, very, very shrouded in snow. Okay, just a bit of the history, and I won't spend too long on this, but Mt St Helens formed during 4 eruptive stages beginning about 275,000 years ago. And it's been the most active volcano in the Cascade range since the Holocene. And as I said, there are about 23 volcanoes in this area of the Cascade, stretching from up in British Columbia, around the sort of Vancouver area, down through Oregon and down to Washington State. And I'm not going to spend a lot of time on all this. As I say, if people want to, they're most welcome to the presentations. The actual bulk of the modern edifice above the 1980 crater floor was constructed in the last 3,000 years. So it really happened in a blip. If you look at the Earth in terms of being 4.6 billion years, the formation of Mt St Helens happened very quickly. And the event that we saw is going to be one of many to come. So, watch out, people, if you're living in that part of the world and if you're around long enough. Again, just to get the setting correct, this is a close-up of the North American plate, which is trying to sort of push south, and the Pacific plate, which is pushing north. Here we have the mid-ocean ridge zone effectively sitting sort of on the edge of the North American plate. And here you can see, interestingly, this Yondafuka plate where the plate here is splitting. So there's this sort of southeast push into the North American plate, and there's also a trench, where my cursor is, which is shown here. And of course, Never forget that just south of this setting is the San Andreas Fault, where the plates are sliding past each other, and you have these huge, or the huge potential for earthquakes once in a while when those plate boundaries move. Across on the right-hand side, again, is just a useful diagram, quite simple. It shows the Cascade range of volcanoes, Mt St Helens, Mt St Hood, Mount Adams, and the plates, and then there's a nice little cross section below here, which shows the actual setting in a cross section. So you can see the spreading ridge, the plate moving across to the east, the subduction zone under the North American plate, the melt pods or bits of magma that are forming at the crust plate interface, and the different volcanoes. That's again a close-up, just gives you a better view of that setting. Okay, let's then get into the body of the show. So this is the setting immediately pre-18. At this stage, it was probably weeks or months before the main eruption. There had been some minor earthquake activity, and you'll see here an aircraft wing where back in those days, a lot of the observation involved regular flights across these volcanoes. They didn't have all the webcams and the laser detection systems and satellites, and of course it was just before the days of GPS. So a lot of the observation going on of the volcanoes would have also involved, sitting on the ground and also flying around the earthquakes to get a sense of what was happening. If we look at the immediate events, or the events immediately prior to the eruption, the first sign of activity at Mt St Helens was a series of small earthquakes from March the 16th. And these earthquakes got progressively more and more frequent and more active as the activity started to build up, and they were probably being caused by hot magma sort of rising into the base of under the base of the volcano. We saw the crater expand, so the whole mountain was starting to be puffed up or pushed up, and the crater was expanding. On May 7, there were small eruptions again. More than 10,000 earthquakes shook the volcano, and the north flank had now started to grow outwards up the stage by about 140 meters. So by May 7, the north flank of the mountain had grown substantially, 140 meters from where it had been, to form a very prominent bulge. And that bulge, from the start of the eruption, or the eruptions and the activity, had been growing probably about 2 meters per day. So we'd ended up with what they eventually called a cryptodome, waiting to fall apart. And that cryptodome was being constructed by magma pushing into the mountain. Okay, so now the photographs get to be quite fun. So this is now Mt St Helens. Looking at it from the north side, you'll see here one of the observers who'd been sort of commissioned or told to go and watch the volcano and what was going on. And you see this massive bulge that had been growing since about March 16 and growing very quickly. So there's the bulge, lots of ridges, fractures on it. Here on the left-hand side is a view from the west. And again, you can see, there was already some melting of water. There was a sort of general buildup and heat of the volcano, and things were getting interesting. Okay, these are two pictures from the time of the start of the eruption. Effectively, there was a magnitude 5.1 earthquake at 8:32 a.m. on May 18, 1980. And again, you can see an aircraft flying around, and we'll comment on that shortly. These guys are probably lucky to be alive, but there's a reason for that. You can see a little puff of smoke. In the middle of that picture, just below the wing, you can see these big fractures across the top of the bulge. And if you look carefully, and it's better on the right-hand side, you can see a little shear scarp forming as this whole north side of the mountain starts to collapse. So these are, if you look at them carefully, just two amazing pictures there. On the right-hand side, you can see that whole north side of the mountain and the original bulge starting to collapse. And here it's already moved, I don't know, probably 20, 30 meters or more. Okay, these are a series of stunning photographs. So on the left-hand side, the earthquake or the earthquakes have now effectively softened up the mountain, and the whole north face is sliding away. And you in this picture, you'll see the start or the formation of this massive earth landslide pushing out sort of at the foot of the mountain, and the structural guys and people like Harry, who's on the call, can tell us a bit more about the energy and the forces that are being or at play in a situation like this. Behind it, you can see this top end of the mountain, and this is where the bulge had been also collapsing. And then just in the top of the slide, top left, you'll see the initial blast or ash eruption starting to happen. And then if you look at the right-hand side, you see a picture again taken from an observer's aircraft, and the actual volcanic event has now started. So effectively, you've had a big door or shutter sort of being pulled away from the north side of the mountain, and you have this whole north side collapsing. And the foot here is the landslide forming. And now you see you've sort of decapped or you've shooken the Coke bottle, and you've taken the lid off, and the vertical stuff here is effectively ash and steam. So the black cloud will be more steam, and the whiter clouds will have a high proportion of volcanic ash and pumice in it. And here in this black material, which is starting to go sort of laterally sideways, is the massive blast that occurred, and it was because of the shape of this of the top of the volcano. Now this lateral blast did tremendous damage for about 30 kilometers on the north side of the volcano. These guys flying in the aircraft were quite lucky that they were at this position and effectively starting to duck around the back of the mountain. So the blasters going off to the north, they were able to duck around the back of the mountain to the south and actually get out of the full force of the earthquake. Had this mountain sort of done a normal type thing and just blown its top, it's quite possible that these guys would still be sort of sitting in outer space somewhere. But they were fortunate, as I say, that most of the initial blast was directed to the north, and they could duck around the back of the volcano. This again shows the volcano really in full action, and you can see the massive steam and ash cloud at the Plinian activity starting to go vertical in the left-hand side, and you can see this massive, more white material, ash and superheated steam starting to blow out laterally to the north of the volcano. If we just go and we'll come back to that, just a quick summary. So at 8:32 on May 18, there was a magnitude or +5 earthquake. The volcano's northern bulge collapses as a huge landslide or debris avalanche. The unloading of the confining pressure removes the cryptodome, and this abrupt pressure release in the volcano allowed hot water in the system to flash to steam. And we had this big sort of slightly whiter activity blowing out in this large laterally directed hydrothermal blast. And then we've also removed and opened up the top of the volcano. So we see a Plinian eruption, that vertical eruption, which went on for 9 hours, starting to form. And then we'll look at this visually, but the massive landslide is still to today the largest debris avalanche or avalanche that we know of on Earth. There might well be avalanches in the ocean that we haven't seen from other older earthquakes, although the seabed mapping is quite good these days. And this north avalanche did a tremendous amount of damage to life and property, which I'll show you. Okay, so this is just that picture again. Just take note of these conifers. These are a couple of 100-meter high conifer trees. There's a big timber industry in the northwest parts of the US for boarding and making boarded houses. You know, most of your West American houses are all made out of timber frames and timber boarding. If you live in an earthquake zone, it's much less dangerous to live in a wooden house than have bricks falling on your head. So this is a spectacular volcano, and you can also see here pieces of bombs and material being thrown out of the volcano, and the big eruption now starting to go at full force in the background. These are two pictures. This is now Mt St Helens from the south. So this is now again later in the morning of May 18. Looking at the Plinian column, and this column of ash and steam reached 24 kilometers in 15 minutes. So a huge amount of energy you get behind a big jet aircraft and you see that sort of energy. Well, this is a similar sort of thing on a much grander scale. And that continued for 9 hours. And I'll show you a bit further on in the slideshow where all this ash ended up. On the right-hand side here is a subsequent Plinian eruption. Pliny the Elder was a naturalist in 79 AD who had experienced or had witnessed the Vesuvian eruptions. So these types of eruptions are named after him, Pliny the Elder. And you'll recall it was this sort of ash and superheated steam that embalmed most of the residents of Pompeii, and I'll show you a picture of that at the end. In fact, the nice thing about this picture on the right-hand side from July 22, 1980, was a Plinian column, so it's blowing stuff vertically, but there's also a very nice, well-developed pyroclastic flow, ash flow, which is sort of spilt over the edge of the mountain and is going down the side. And we'll look at some of the deposits formed by a pyroclastic flow like that. And that's probably exactly what happened in the Vesuvius eruption and the destruction of Pompeii. Okay, moving on, just to try and put this in a nice simple diagram. This shows you the mountain as it was, 2,950 meters at its summit prior to the main eruption, the vertical ash plume, this violent lateral explosion, which did, as I said, tremendous damage, and then the collapsing avalanche. And below here is what the volcano subsequently looked like and still looks like today. And Adrian Reynolds, who's on the talk, was there in 2011. He can tell us a bit more about how the volcano looks now compared to how it looked back in 1980. This diagram is very telling and shows the effects of this volcano, particularly sort of in the surrounding area. So here, and there's a sort of blown up version on the right-hand side, but if we look at the left-hand side diagram, it's not very clear, need to fix it, but you'll see where my arrow is, you'll see the actual crater zone. And you'll see down the rivers or anything that was sort of low-lying or potentially a stream or river, particularly the Toutle River. So there's the Toutle River, which heads out west of the volcano. And there's the North Fork, and they're all filled with these brown lahar deposits or basically mud flows, which were a combination of all the suddenly melted water, ice, snow, locked up or sitting on the volcano. So you push all this hot magma at 600 degrees and thereabouts into it. All the water that interacts with the volcano flashes to steam, and you get vesiculation of the magma to form the ash and pumice. But anything that's heavier is now caught up in all this molten water. So aside from the fact that you had enormous damage to the north due to this pyroclastic debris current or blast, you also had these mud flows or lahars, which went miles down the river, and I'll show you pictures of some of the consequences. So that was very destructive. All around to the north here, and if you look at the scale, if you go up, look here where it says Green River, so for about 25 to 30 kilometers north of the volcano and north of the crater, basically, there was this massive lateral blast and huge amount of destruction of timber and property and life. And then interestingly, this yellow stuff here is the debris avalanche. You can see there, so that was the avalanche that we saw forming. And what you don't see here, but we'll see it a bit later, was the pumice flows. Okay, so this is now a picture out into these northern areas, sort of directly north of the volcano, the volcanic vent, across this gray area. And this is the big cedar forests that were flattened by that blast. There's logging equipment, a big bulldozer, and a big truck that they use to move the logs, just been tossed around like dinky toys. Down on the right-hand side, to give you a sense of scale, you can see these big cedar logs. They've been sort of blown out the ground. You can still see the roots on the one in the middle. And for scale, you'll see two park rangers who were in the area a couple of days after the eruption, inspecting the damage. So there's two grown-up human beings for scale. Quite spectacular to see the devastation and the scale of devastation. Just to comment, the company, the logging company here was the Weyerhaeuser Timber Company. Not going to go through all of that. The area of destruction or devastated was nearly 68,000 acres, about 14% of their holding. It damaged 36,500 acres, and I'm sorry, I'm talking about acres of marketable timber. Damaged and filled up 5,500 acres of lakes, streams, and lands, and ruined 3 logging camps. And the rest here is really about how they then salvaged the timber. So by October 1980, the company was back in there moving these blown down logs on a huge scale every day. They saved 850 million board feet of timber. It doesn't mean a lot to me, but that's enough to build 85,000 three-bedroom houses. So a huge amount of damage, but fortunately they were able to recover a lot of that material. And they then, once they cleaned out and taken out all these logs, they began with the replanting program in 1981. Okay, let's look at some of the deposit types. This is just a good slide. It's actually part of a video. That video clip is shown at the end of the presentation. People can look at it. But this here is a nice cross-section, sort of lower down from the volcano, showing the airfall tephra deposit. So that this here would be the debris and the pumice, and you can see big rock clasts from the airfall deposit. So this is the material that initially got blown up vertically and then deposited locally. The fine ash obviously got blown and caught up in the jet stream, and a lot of that ended up way down to the southeast across the US. Here, by comparison, is a pyroclastic flow from June the 12th, 1918. You can see how bedded this material is, very different to the airfall deposit. And then on the top here is a mud flow. This black material is a mud flow, and that again is from a later eruption of Mt St Helens. On the right-hand side there's a lovely example of a pumice flow. So that the very light material, that vesiculated magma and pumice, also in a sense was able to flow. If there's enough of it, it gets quite dense. And there was a very big pumice field that formed in the front of the mountain, which I'll show you. This is what lahars do, or mud flows. So this is a solidified mud flow which covers, if there's a depression or an area that muddy water and water can follow, it'll follow it. So it got onto the State Highway 504 here near the town of Toutle, and covered this sign. So this sign was originally on the road, and you can see a fully grown geologist standing there, and you can see how thick the mud flow has been, and it's like sort of wet cement. When it stops and when it settles, it forms this nice hard layer that you can then go walk about on. And here on the right-hand side is effectively cross-section of an old mud flow. Looks like a gravel, very hard, very cemented. Okay, that's just a schematic again showing how the volcano looked post the eruption. As I said to you, there was a big pumice plain at Spirit Lake here on the right, on the left-hand side. The landslide deposits, and bear in mind, this is the area we're looking directly from north to south. That the area that got cleaned out and devastated by that lateral blast. This is the ash material that got spread across the US. As I say, the jet stream up there is typically west or northwest to southeast. And so anything that was light and got into the stratosphere ended up being blown across the country. some of it quite thick, some of it quite thin, but very extensive. And there on the right-hand side is another example of ash spread around in an earlier eruption of or later eruption, I beg your pardon. Okay. Definitions, I'm not going to go into that, but I did talk about these pyroclastic flows and surges, and they called them in the good old days nuidentes, so they're hot incandescent clouds of gas and ash. And this is a picture, some of you might have been to Pompeii and seen the devastation that the nuidentes caused in 79 AD. And people, of course, the houses in those days wouldn't have had windows, so people, sleeping at night were basically entombed by this hot gas and ash, and that's where they still lie. In terms of the casualties, there were 57 people died in the eruption. Fortunately, Mt St Helens then and the general area was not that populated. David Johnston is quite a legend. He was a volcanologist and observer on the day, and he saw this whole event happen. And sadly, he expired at 8:32 a.m. On the morning. He radioed and Vancouver. This is it, and this is not Vancouver in BC. This is a small town where the USGS volcanic observatory is, south of Seattle. So that's where they still monitor the earthquakes today. So he did not survive. The cold water ridge that he was sitting on was later renamed Johnson Ridge. And there on the right-hand side is the US National Guard identifying bodies. Photojournalist Reid Blackburn, same thing. He didn't make it. He'd been working for the press, National Geographic, and the USGS as an observer. He was camped at Coldwater Creek, 5 kilometers from the north side of the volcano. He managed to get to his car, and he was found effectively asphyxiated in his car 4 days post the eruption. There were thousands of animals, probably something like 7,000 big game, deer, elk, bear, small mammals, many small mammals, birds, and fish were killed. And sadly, I think these 2 horses, which the 2 Brown brothers at one stage were trying to rescue from the overflowing Toutle River, which was also a mud flow. You can see big boulders that had been carried down it. They tried, and then suddenly they encountered the river rising. And in this picture on the right, you can see the 2 of them still at the back, and 2 colleagues who'd been trying to sort of assist with the rescue, running away down this train before they got drowned. And the horses, I think, ended up drowning. Property and timber, this is again a big mud flow on the left-hand side, which has engulfed a house. The timber and the big vehicles on the right-hand side we've seen. The eruption volume and statistics on the left show you just the scale. And the important thing to take note here is that Mt St Helens, although it was very spectacular, was actually quite a small eruption. So if you look at it in comparison to, say, Vesuvius and Krakatoa, Mt St Helens is not that large. But the avalanche, for example, there was about 2.5 cubic kilometers of debris moved, 3.3 billion cubic yards, or 1 million Olympic swimming pools. So lots of dirt moved out of that side of the mountain, and the amount of ash that fell was about 540 million tons, fell over an area of about 57,000 square kilometers. Just to go and look at the work that's ongoing, and the hazard monitoring and prediction obviously has become more and more of a science. It's not particularly quantitative yet, but it's certainly a great deal of work being done on, but particularly an area like this. I mean, there's Seattle. Seattle is a very big, if you look on the right-hand side of the map, if you can see Seattle where my arrow is, there's a very big industrial area. Boeing's world's biggest factory, I think, is there. Tacoma is effectively a satellite or bedroom area for Seattle. There's Mount Rainier, and there's Mt St Helens. So, and if you look at the diagram table on the left-hand side, you'll see that the two most active volcanoes in that area have been Mount Rainier and obviously Mt St Helens. So according to the volcanologists in this table or diagram, people consider Mount Rainier to be probably one of the greatest threats to this northwest part of the states. And here, it, again, is a similar diagram to what I showed you previously, Mount Rainier, and all of these yellow and brown stripes are basically the drainages running off the volcano, and where you've had previous and historic lahars and damage to what was, back in the times of previous eruptions, quite a poorly or lightly populated area. But this now is an extremely highly populated area. As I say, it's effectively sort of a dormitory city to Seattle. So lots of people live here, and were there to be a major eruption of this mountain, which again is over 1 kilometer higher than Mt St Helens, you could have fairly catastrophic consequences on this area and the population. Okay, so this is the mountain as we see it today, very serene and impressive. This is a picture close up of, excuse me, of the crater. So there's a crater that's formed and a small rhyolitic dome post the eruption. Steams, lets off steam once in a while. So, this volcano is not dead by any means. Obviously, the monitoring today is far more sophisticated. This is a satellite construction of the volcano. This is from 2015. You can see the volcano itself quite nicely. You can still see the damage zone showing up, although that's starting to be revegetated, Spirit Lake. And obviously with GPS and laser and satellite imagery, they keep a very close watch on all of these volcanoes. Just to finish off, and for interest, so this is the rather spectacular volcanic ash airfall deposit that I also worked on at the south end of the Mkuzi Game Reserve. There's the Lubombo Mountains on the right in the map from Mpongeni all the way up to the Limpopo. A very thick sequence of basalts and rhyolites, and down here at the bottom right-hand corner is a very spectacular, gorgeous volcanic complex. And I think some of there's Nigel Hicks on the call today. He and his team out of the CGS have been doing some remapping and work down there, which is fantastic. But really, really spectacular example of an airfall deposit, and you can see how bedded it is. And if you look up close, it's also graded. Okay, so that's Mt St Helens, just the most spectacular volcanic event. It happened when we could see it happen. Very well documented. For anyone who's interested, I've got lots of literature, including a 500-page memoir that was produced by the Geological Society of America in 1981. So, as you can imagine, there was a huge amount of work done by many people on the deposits and the events and the record of earthquakes, etc., etc. So if anyone's looking to learn more about volcanology, I've got lots of stuff I can pass on to. So thanks everyone, and I look forward to some discussion.
Thank you very, very much, John. You guys can put on your mics again and your videos and raise your hand or just start speaking. Got a message here from Jean and Anita Simmons. It says that great slides, brilliant to get a refresh on volcanism again. Love the great emphasis on that water plays, water everywhere, but not a drop. And the bulge formation being a great tool for early warning and preparedness planning. Right, Andrew, anything from your side?
Yeah. We want to comment from Adrian. Adrian, what you saw it in 2011 and being revegetated, and that also made a sort of a national park in that area, sort of in front of the volcano.
Yeah, it was very interesting. I mean, it is revegetating, except where there's thick layers of ash, and nothing will grow through that for another few thousand years, I guess. But actually, very pretty away from the ash. And within the national park, I would say no attempt to rehabilitate. The lake there, as you mentioned a couple of times, it's a superb, beautiful looking lake, and it's 1/3 full of logs that are still floating on the surface and slowly decomposing. And the Parks Board take the attitude, and it might be partly financial, but this is a natural event, and we'll let nature take its time to rehabilitate it all. But really superb. Lots of how can I say, show and tells. The park rangers have talks every hour or so, and they'll stand in front and they'll take you through the whole thing. Not as professionally as you did it, but they give a fair understanding of what went on. Absolutely lovely. And the previous day we'd been at Mount Rainier, and that was just gorgeous. Wildflowers, absolutely looked beautiful. And then you go to Mt St Helens the next day and you think, ooh, what happens if that happens just up the road in Mount Rainier one day? The other thing that came across there, and also from your talk, was that there's guys looking at this bulge, and they're measuring this bulge developing and developing and developing. And I guess it's easy to say in hindsight, but I'd get into my 4x4 and I'd drive in the opposite direction as soon as I could. But super, John. Thanks very much.
Okay, thanks, and thanks for the update. But Adrian, you also make a good point. I mean, we too have these amazing geological exposures in our country, and we definitely need to do a bit more about marketing them, and getting school kids to go and look at them and understand them, etc. So yeah, it's a sore point for me.
Yeah.
So how fine-tuned are the warning systems now? I'm just thinking back to the mining days, like there's an increase in seismicity, and then when do you actually call the shot? When do you say, because you've got to produce. So when do you say, look, this is now getting too dangerous?
Mm-hmm. Yeah, and it's a good question. I mean, I think there is more that when obviously the amount of data they'll be collecting, I'm sure they've got some big computer capacity, and if you speak to the experts today, and I think Harry is still involved with the deep level seismics. They do have sort of benchmarking where they think that's certainly not an exact science, but think if there's this sort of episode of earthquake activity, that they can start to issue early warnings. And I guess the real problem though, as you can imagine, issuing an early warning, and everyone, then gets in their cars and starts going somewhere, the chaos that would also cause. So I think it's one of those extremely difficult, processes of, when do you pull the trigger? But if anyone's got any comments on it, would be most interested.
Now then, if you do get an early warning and you go away, nothing happens, how do you now determine when you can go back?
Yeah. No, that's always the problem. It's like the big fires. You see what happens in Australia, for example, and in the Western US. When do you pack up and go? Because you think the wind's going to change. So we creatures of habit. Nigel, have you got anything to add? You looking at the Southern Lubombo there very actively, so and I'm quite open to being proved wrong, and all my interpretations have hopefully gone out the window. So I hope you guys are having fun there.
Thanks, John. Hi, everyone. It's great to be on the call with you guys today. Very, very interesting talk. Thanks, John. Yeah, well, from a CGS perspective, we've been doing a whole lot of mapping up in the Maputoland area, predominantly looking at the Cretaceous stuff and the Cenozoic stuff on the Maputoland plain. But associated with that, we've also gone into Mkuzi and Pinda and had a quick look at what John was doing there. We obviously can't get out of the cars that much, so we weren't able to do as much detailed mapping as what John did. It's unfortunate though that that amazing photo of the ashfall tuff that he showed is no longer. It has been mined out from Pratley's mine. So they've opened up a big zeolite quarry there. There's still some amazing exposures and everything, which I'm busy sharing with John. So hopefully we're going to have a publication out on that in South African Journal of Geology in the next year or so. But no, I mean, my big thing is that it's such a dynamic sort of environment. If you look at Mt St Helens with all of the ashfall tuffs and the pyroclastic flows and the lahars, that to try and create a true volcanic stratigraphy that you could put into, say, the lithostratigraphy of South Africa, it's really, really difficult to do. So, and we don't have any experience of that sort of stuff in South Africa. I mean, we've got none of the volcanoes like you see at Mt St Helens. So it's really interesting to try and work on that sort of stuff. We can't really get up to John's level that he had in his mapping in his PhD and his MSc, but we're getting close because we've also got new high resolution aeromagnetic data that was flown in 2018 over the entire plane. And that has really brought out a whole lot of new ideas on the Bombeni Ridge, which extends northeastwards from the Bombeni volcano, and mapping of that, as well as on the field, in the field mapping, has brought up some new ideas that we want to bounce off John. So yeah, so it's been really interesting.
Fantastic. Good to know that people are re-looking at things. We need to do a lot more of it. Yeah. Okay, anyone else? Bastian, are you got any comments, or are you going to tell us all about
But I love it. Direct
next week?
Yeah, I think I'm presenting next week. Is it right?
Yeah. We look forward to that as well.
Your presentation gave me a lot of insights, because some of this explosive activity is what we can see at the bottom of the Karoo. So my question would be what, first I would like to know, how do you form the mountain in the first place? And is it normal for a volcano like this to evolve into a more, what did you call them, basalt, thin flows? So is that the normal evolution, to start with explosion and then to become more basaltic, I guess?
No, Bastian, I mean, this is all very silicic. If you look at all of those volcanoes and the Cascades, you know, there's the occasional sort of andesite flow, but I would imagine, and it's a good question, they start as, you know, probably rhyolitic domes. And you know, the nice thing, and I didn't show the picture, but I'll send it to you. If you go and look at the sort of whole north side exposure now, you can actually see and they've dated them. Obviously, you know, when you have exposure like that, and with dating, you can actually date each and every unit quite precisely, and they can see the sort of construct. So you can see, you know, a combination of, there's a rhyolite dome that's been decapitated by an explosion, and then there'll be an overlying, you know, ash flow. And you know, that I think just builds up over time, as I say, in this case, 270,000 years, which, you know, they've worked out quite precisely. And that's the way, you know, these things build up, and bearing in mind everything's so sticky, you know, it doesn't flow away. So in comparison to your basaltic Hawaiian situation, big flat, you know, sort of stratovolcano, because everything's so liquid, you know, in this case, you know, the stickiness means it all sort of builds on top of each other. But I'll send you some more information and another diagram or two, which sort of shows the progressive construction, and it's all sort of vertically orientated compared to your horizontal basalts in the Karoo. And I guess.
Go ahead, Nigel.
Good night.
Thanks, Henny. Just to follow up from what Bastian was asking there, I've got a question as well, because if you think of the stuff locally in the Karoo, I mean, you go from massive voluminous basaltic volcanics into rhyolites of the Lubombo, and then again you get a repeat of the same package in Mozambique, where you go then into the Movaine basalts, and then you've got overlying rhyolites again, sort of with the Bombeni stuff. Is you're obviously having changes in the composition of the magma as it's evolving. So it would be interesting if John has any ideas as to how you get the cyclical sort of pattern forming in the Lobombos here. Like, what's causing that cyclicity? Like, would that be changes in the extension? I mean, obviously the Lobombo itself is supposed monocline from, I can't remember who came up with that. I think it was McCarthy and those guys. And then is there a change then again to a different form of extension? Like maybe when the Agulhas-Borkum fracture zone started extending, that you have much younger cyclicity then from, again, basalts through into rhyolite. Do you see that in the States at all? Because I mean, that's a compressional environment rather than extension.
Yeah, it's really interesting. And I think it's exactly that. So you had sort of, and we see it, I guess, again, to some extent in places like Ethiopia and their big volcanic or basaltic volcanic fields. And you see it also very nice in the Snake River plain, and I didn't talk about it here, but in that sort of general area further inland of the Snake River basalts. But in the Lobombo, you actually, interestingly, almost started with a kimberlite at Dokawaya in Swaziland, which is 205 million years, and then you had some nephelonites, which are also sort of fairly deep-seated alkalic rocks. And then you got the massive outpourings of basalts. And I suspect there was also a lot of underplating, we think, that happened in that basaltic outpouring. I mean, when you pour out that amount of basalts, and remember, there you see about 5 kilometers of basalt, and we see it again in the bushveld. You probably had underplating of a more sort of residual rest state. And then and you still have a lot of heat flow in the system, and that then melted to form what looked to be very high temperature ash flows, which welded themselves into those amazing Lobombo mountain flows. And then, you probably, as you say, you give that rift another jerk, and it sort of opens up some more, and you go back to melting sort of deeper material back in the mantle or upper mantle, and you produce the basalts. But it's interesting that most of these, big what we call large igneous provinces, lips, do have cyclicity, and that must be related to perhaps the structural events going on at the same time. And the fact that I looked at it from a fairly one-eyed point of view, just the volcanism. You guys have been looking at the structure and the different structural events that have happened around sort of that east coast of southern Africa. And look forward, and I'm sort of passing the question a bit, but look forward to seeing how your bigger picture looks at the end of the day. Right. Anyone else?
John, is there a model that shows the epicenter of the Ventersdorp, how it originated, where, did it come through several vents? Was it a major opening somewhere? I don't have the background to that.
Yeah, good question, Henny. I mean, we're actually going to, we were speaking to Gerard Meintjes the other day, and he's Mr. Ventersdorp. Aside from his interest in the mineral deposits in the Makwaland, he spent a lot of time in his younger career studying the Ventersdorp, he and a few of his colleagues at University of the Free State. And the Ventersdorp is actually, a great deal more extensive than we think. We've looked at it very extensively where it overlies the Wits for obvious reasons. But you get what they call the Kanya volcanics in southern Botswana, and they are almost certainly another portion or another basin of the Ventersdorp. And if you look at our Karoo, and Bastian will talk about the central Karoo, Lesotho next week, but the stuff over in the Lobombo, the basalts at the base, the Lobombo flats or the Swaziland flats are all basically the same basaltic rocks that you get in Lesotho. And then, of course, you get the Springbok Flats, which is another basin with Karoo lavas. And then if you go across to Edendecker and northern Namibia, there's a massive sequence of younger but still equivalent Karoo rocks in Ettendecker and put the continents back together, and the lava flows or the basalt flows and the rhyolite flows that you get in the Ettendecker in Namibia, you can match them perfectly to the stuff in the Paraná Basin, which is now sitting across in southern America. So these, these big volcanic events, like particularly the lips, tend to sort of, form big basins, big flows, wherever there's, a depression, wherever magma, can make it to the Earth's surface. Ventersdorp is another fascinating, 2.7 billion year event. Okay. Yeah, there you go. Nigel's just said that their dike swarms in southern, where's it, Infolosi area, that are the same age as the Ventersdorp again. So that's way out in eastern KZN.
Okay, guys, it's time for closing up. Any last questions? Thank you very much for an interesting conversation, guys, and well done, John.
Okay.
So
right,
we'll
great.
next Thursday.
Yeah, and we'll gladly send the presentation or distribute it in our monthly little note. Yeah. Thanks, guys. Thanks, everyone. Enjoy the rest of your day. Thanks, Nigel, for your input, and thanks, Henny, for managing the show again. And we look forward to seeing Bastion next week.
Okay. So all our talks are on the GSS platform with YouTube. And there's a playlist that we regularly send the link to, so you can go and visit and go back to any one of the ones that we've had so far. Thanks, everybody. Good day to you all.
Thank you, John.
Thanks all. Go well.
Cheers, John.